Good afternoon. Good afternoon. Good afternoon. Okay, Prof. Oh, good. So, Brian, are you able to hear me?
Yes.
Okay, good. Are you also able to see my whiteboard? Is my whiteboard visible from it?
Yeah, good.
Ah, good. Yeah. So we are going to discuss about linear recurrence relations. Sometimes they are also called difference equations. So majorly in this course, we deal with recurrence relations with constant coefficients. So when you uh, go to higher levels, we'll discuss general recurrence relations, which have also variable coefficients. But as an introductory course on the discussion of recurrence relations, we'll majorly deal with relations whose uh, coefficients are real numbers or constants. So begin by defining a recurrence relation and then give examples and see how we can solve recurrence relations. So linear recurrence relation so a linear recurrence relation a linear homogeneous recurrence relation of degree k with constant coefficients is a recurrence relation of the form an equals to C1 an minus 1 plus C2 an minus 2 plus C3 an minus 3 all the way up to plus ck an minus k, where this number ci's are real numbers. And for this to be a kth degree recurrence relation, ck must be non-zero. So this is how we define a linear homogeneous recurrence relation of degree k with constant coefficients. Is an equation of this form or a relation of this form. So let's call this one so 1 is said to be linear because the right-hand side is a sum of previous terms of the sequence each multiplied by a function of n. Then 1 is homogeneous because no term or terms occur that are not multiples of the AJs. And then 1 has constant coefficients since all the coefficients are real numbers. Rather than functions that depend on n. And then 1 has degree k since an is expressed in terms of the previous k terms of the sequence. So then now we can give examples to see which recurrence relations are either linear or nonlinear. Examples. So if I have Pn equals to 1.2 times Pn minus 1, is this linear or nonlinear? Is this recurrence relation linear or nonlinear? Please unmute and say the answer. Is this linear or nonlinear? Is this linear or non-linear? Linear, correct? Do we say it has constant coefficients? Does it have constant coefficients? Does it have constant coefficients? Yes or no? Okay, what is the degree of this recurrence relation? Okay, maybe you are still confused with that. So let me give you another, maybe probably you can get
Other examples.
So if I have an 2 an minus 1 plus 3 an minus 2, and then I have 3 an equals to an minus 1 plus an minus 2. And then I have another one 4 an equals to 3 an minus 1 plus 4 an minus 2 plus 6 an minus 3. So what is the degree of the recurrence relation in 1? Or what is the degree of, if not 1, what is the degree of the recurrence relation in 2? What is the degree of the recurrence relation in 2? So check, this was the definition. That if we have a recurrence relation of the form given in 1, then this is a linear homogeneous recurrence relation of degree k with constant coefficients. And we have gone further and explained why we are calling this linear, why we are calling it homogeneous, why we are calling it constant coefficient, why we are saying it has degree k. So what is the degree of the recurrence relation in 1? What the degree?
Excuse me, Mr. Ananga, you said K back back in okay.
Yes. So what the degree of the recurrence relation in a 1? So, okay, what's the value of k in 1? You are attacking it in the correct way. So what's the value of k? If you relate 1 and the general, sure. Check the way the general linear recurrence. So what's the value of k in 1? Is it 1 or negative 1? 1. So yeah, so the value of k is what determines the degree of the recurrence relation. So the degree of the recurrence relation in 1 is 1. And the degree of the recurrence relation in 2? Yeah. So remember, k is the number of previous terms that an is represented, is used to, is expressed with. Okay. Let's go back to the definition. We are saying that a linear homogeneous recurrence relation of degree k with constant coefficients is a recurrence relation of the form given in 1. So we have an equals to C1 an minus 1 plus C2 an minus 2 plus C3 an minus 3 all the way up to plus ck an minus k. So when a recurrence relation is in this form, we call it a linear homogeneous recurrence relation of degree k. And then we have gone further and explained point by point why we are calling it linear, homogeneous, and then why we are calling it has a degree k. So the k value in 1 is actually 1 because we only have Pn is expressed in terms of the previous Pn minus 1. So this is a linear recurrence relation of degree 1. And then what is the value of k in number 2? What is the value of k? Okay, explain, yes. Mm. Mm. Okay, wrong answer. It's a wrong answer, but good for learning purpose. So, what is if I tell okay, forget these things are very hard. Forget about them. If I give you 2 goats plus 4 cows, how many cows do we have in total? And how many goats do we have in total? 2 goats. Good. So then when we have, remember, an is a sequence, an minus 1 is a sequence, an minus 2 is a sequence. So you cannot combine an minus 1 and an minus 2. These are actually totally independent things. So it'd be very wrong for you to say that we are combining 2 plus 3 is 5 and then putting n minus 1 and n minus 2 together. That's not how we interpret them. So the an minus 1 and an minus 2 is like the example you're giving goats and cows. So you cannot, you can only combine them if we have the same subscript. It's like if someone tell you what is 2x plus 3y, you don't say it is 5xy or 5y or 5x. So the an minus 1 and an minus 2, they are independent sequences. So you can't combine them the way you are saying. Yeah, that should be obvious because you see, the way this one is actually, you can actually relate it to what we have in the general form. This is C1. C1 is a constant, then a sequence an minus 1, plus C2 is a constant, an minus 2, plus C3 is a constant, an minus 3, etc. up to plus ck an minus k. So what determines the value of k is this number here after n minus, the largest of it, or largest of the numbers we have. N minus now the largest value is what is the value of k. Yeah, so the degree of the second recurrence relation is degree 2. Is it homogeneous? It is, correct. And then number 3. What is the degree? Degree is still 2. Number 4? 3, correct. So another definition, a linear non-homogeneous recurrence relation of with degree k with constant coefficients is a recurrence relation of the form an equals to C1 an minus 1 plus C2 an minus 2 plus C3 an minus 3 all the way plus ck an minus k plus f of n, where C1, C2, all the way up to ck are real numbers. Ck is non-zero, and f of n is also non-zero. So if we have a recurrence relation of this form, so call this one 2, then it is called a linear non-homogeneous recurrence relation of degree k with constant coefficients. So the non-homogeneity comes from this function, f of n. So if this is non-zero function, then such a recurrence relation is said to be non-homogeneous. So for example, if you are given an equals to 2 an plus an minus 1 plus 3, if I have fn equals to 2 fn minus 1 plus 5 fn minus 2 plus n squared, this is non-homogeneous. If I have bn equals to 4 bn minus 1 plus 6 bn minus 2 plus 2 plus 3n plus 5, this is still non-homogeneous. So non-homogeneous simply means that in the equation, there will be a term which does not depend on AI values. Am I clear? Yeah. Yeah, so then now, when we have product of the AI values or powers more than 1, then such recurrence relations are called nonlinear. So for example, if I have a recurrence relation of this form, for example, an equals to 3 an minus 1 plus an minus 2 power 3, or I have an equals to 4 an minus 1 squared plus 6 an minus 2. All these are nonlinear. Nonlinear because these terms with AIs, some of them have powers more than 1. Like here we have a power 3, an minus 2 is to power 3, here an minus 1 is to power 2. And also, even if I have another recurrence relation of the form, say 6, an minus 1, an minus 2, plus an minus 3. This is also another example of a nonlinear recurrence relation, because in this relation or in this equation, there is a term which involves product of AI values. So where we have product of AI values, or the powers of AI values is not 1 or more than 1, then that makes the recurrence relation to qualify to be called non-linear. So for linear, there will be no such product of AI values, and all the AI values will always have maximum of power 1. Or really, it's either it doesn't exist. There is no AI term raised to any other power apart from 1. So I hope now you should be able now to classify in terms of the nonlinear and non-homogeneous and homogeneous. Is that true? From those few examples? Okay, so sometimes you can be given some few values of the AI values, and then you're asked to generate others. So for example, given that A naught is given by 2, find A1, A2, A3, A4 in n equals to 4 an minus 1. So remember, a recurrence relation means that the terms are given in such a way that the next term depends on the previous term or previous terms. So for example, here we are being told that the value of A naught is 2 to find A1, A2, A3, and A4. So this means that when n is 1, our relation will be A1 equals to 4, A1 minus 1. So which will be 4, 1 minus 1 is? What the value of 1 minus 1? What the value of 1 minus 1? If you participate, I'll finish this class earlier than usual. If you don't, I'll have to extend more than 3 hours. But if you participate, then I'll stop earlier. 0. So, and then we have been told that A0 is 2. So this will be the same as 4 times 2. So the answer will be? Eight. Then when n is 2, so I'll have A where there's n put 2, equals to 4, A 2 minus 1. So 2 minus 1 is 1. So this will be 4 times. 4 times 8, because we have A1 from the previous step, correct? So what is 4 times 8? 32, correct. Yeah, and then when n is 3, we have A3 will be 4, A3 minus 1, which is 4A squared, And the value of A2 is 32. So 32 times 4. 128. And then when n is 4, we have A4 will be 4. Where there's n, you put 4. So 4 minus 1. This will be 4. A3. So A3 previously is 128. So 4 times 128. What then? 512, correct. So that is, say, problem 1. And then problem 2, given A0 is 0, A1 is 1, and AN equals to AN minus 1 plus AN minus 2, find A2, A3, A4, A5, A6, A7, AH, A9, and then A10. So here, you say by definition, AN is AN minus 1 plus AN minus 2. So when N is 2, so I'll have A2. So where there's N in this formula, you put 2. We'll have A2 minus 1 my plus A2 minus 2, which is the same as A1 plus A0. Because 2 minus 2 is 0. A1 we have been given as 1. A0 we have been given as 0. So the value of A2 will be
1.
1, correct. Then when N is 3, so I'll have A3 equals to, so just putting N values for 3 in this formula. So we'll have A, which is A2 plus A1, correct. So A2 we have 1, A1 we have 1. So the answer will be 2. Then next, N equals to 4. So A4 will be equals to, when you put A3 plus A2. So A3 is 2, A2 is 1. So the answer will be 3. N5, we have A5 equals to A4 plus A3. So it should be 3 plus A3 is 2. So the answer will be 5. So can you get for me the value of A6? So I have 8. And what is A7? 13. What is A8? 21. A9? 30. 34. And then A10? 55. etc. So this number forms a pattern we usually call the, produces a pattern called the Fibonacci numbers. So these are Fibonacci numbers. So if you are doing ICT, Fibonacci numbers is not a new thing. So this recurrence relation AN equals to an minus 1 plus an minus 2 with a not 0, a 1, 1 generates numbers we call the Fibonacci numbers or Fibonacci sequence. So that is so. Similarly, you can be given a different. For example, if you are given, say, a naught is 2, a1 is 3, and an is given by an minus 1 plus an minus 2 plus n squared. Find a2, a3, f1, f5. So if this is the case, it is the same way we have done the previous two problems. You say when n is 2, then your formula will be a2 equals to a2 minus 1 plus a2 minus 2 plus 2 squared. So where there's n, you are replacing by 2. So this will give you a1 plus a naught, 2 squared is 4. Then you just substitute the values of a naught and a1. So a1 is 3, a naught is 2, and a4, and the other part gives 4. So when you get the sum, a2 will be 9. Then when n is 3, you write the same formula where there's n put 3. So I'll have a3 equals to a3 minus 1 plus a3 minus 2 plus 3 squared. So this will be a2 plus a1, 3 squared is 9. So a2 we have obtained as 9, a1 is given as 3, then this is 9. So what will this give us? $21. Then in a similar manner, you can generate the other A4, A5, A6, etc. And so one of the key things that you can observe from these 3 examples is that for you to get A2, like in this problem here, you need to know the value of A1 and A0. For you to find A3, you need to know the value of A2 and A1. So if you don't know the value of A2, you will not be able to get A3 with this given recurrence relation. So similarly, for you to get A5 in this recurrence relation, you need to have known A3 and A4. So an answer to the value in the recurrence relation depends on the previous values. So if the previous values you obtain are wrong, then obviously what you calculate is also will also be wrong. So you have to be very careful so that you don't make any mistake, because the results which you find at every step depends on the previous values you obtain. So once we have known what a recurrence relation is and known how to generate various terms in a recurrence relation, let's see how recurrence relations. And the same way, okay, I hope this group, you did estimate. I don't think those 306 ordinary differential equations. Did you do that? Have you done ordinary differential equations? Must be second or third year.
Yes, we
Yeah,
did.
good. Yeah. So the way we were dealing with ordinary differential equations of higher order is the same way we are going to deal with recurrence relations when it comes to solving. So briefly, and we'll actually realize that the work is actually not as complicated as it might seem to be. It's exactly the same process we did for solving higher order differential equations. So subheading, solving linear homogeneous recurrence relations with constant coefficients. So if you remember what you did in SMA 208 in second year, it is the same structure we followed when we were dealing with differential equations of higher order. We start by solving homogeneous equations. So consider the recurrence, the relation an equals to C1 an minus 1 plus C2 an minus 2 plus C3 an minus 3 all the way up to ck an minus k. So if you remember clearly from the start of this class, this is what we define as the linear homogeneous recurrence relation of degree k, constant coefficients. So consider this recurrence relation. So we assume, so call this one 1. Assume that the solution to equation 1 is of the form an equals to r power n, where r is a non-zero constant. So we assume that the recurrence relation. If you can do the relationship with what you're doing in SMA 208, you started by saying that we assume the solution of the differential equation to be of the form e raised power rx. So here now for the recurrence relation, we are assuming that solution an is r power n. And you know what, when you say a solution, then it means that when you substitute into the equation, it must satisfy the equation. So if we are saying that an is r power n, what would be the value of an minus 1? In terms of r, how will the solution look like? If an is r power n, what is an minus 1?
R power n minus 1.
Correct. R power n minus 1. And then an minus 2? Correct. A sub n minus 3? N minus 3, correct. So this follows up to when we have a sub n minus k, the solution will be? Correct, r power n minus k, good. So then we are going to substitute this into this equation, because now when you say it's a solution, then they must also satisfy the equation itself. So where there's a power n, we replace by r power n. Where there's a n minus 1, we replace by r power n minus 1. Where there's a n minus 2, we replace by r power n minus 2. Where there's a n minus 3, we replace by r power n minus 3. all the way up to where there's an minus k, we replace by r raised power n minus k. That's what you have when you make that substitution. So then now, since we have already restricted that r is a non-zero constant, then all these numbers are non-zeros. So if I call this one equation 2, so dividing 2 by r power n minus k, we have r power n over r power n minus k equals to C1 r power n minus 1 over r power n minus k plus C2 r power n minus 2 over r power n minus k plus C3 r power n minus 3 over r power n minus k all the way up to plus ck r power n minus k divided by r power n minus k. That division is justified because r is non-zero, and so any power of r is a non-zero number. So division by non-zero numbers is allowed. So from laws of indices, what would be the simplification of the left-hand side? What would be the new power of r?
R power n divided by n.
So when you simplify, just check. Do the long process, just use laws of indices. When you say A, if you remember from your Form 2 work, if I have A power m divided by A power n, then I have A power m minus n. So do or apply that property to the powers we have and tell me when you simplify what will be the new power of r. This might be the only proof you can provide in my exam. So apply this law of indices to this and tell me what would be the simplified expression and what would be the power of r.
R will be negative.
Huh? Will be? R power k, correct. R power k. And then C1, what would be the new power of r in this other term? I hope everyone knows where the k is coming from. There's no miracle being performed. Good. So then now, can you simplify the next part and tell me C1 r power? So it's the same thing as when you as we started the term. So we have correct k minus 1 plus C2. What will be the new power of k? New power of r? So remember what people are doing is simply take this power n minus 2, subtract n minus k. So it'll be n minus 2 minus n minus is plus k. So these and these cancels out. So the answer will be k minus 2. Then plus C3 R power k minus 3, correct. And then plus all the way up to CK R power. What will be the new power of R? Or is simply, so just one, okay? Yeah, so that just will have CK. So then we can rearrange this, rearranging. We get, so we'll have R power K minus C1 R power K minus 1 minus C2 R power K minus 2 minus C3 R power K minus 3 minus CK equals to 0. So this equation is called the characteristic equation. This is the characteristic equation of the recurrence relation 1. So then now when you solve this characteristic equation, maybe call this one 3. When you solve this characteristic equation, then we get the solution of the recurrence relation. So I'll pick a smaller case of K. So when K is 2, so when K is 2, equation 3 becomes R squared minus C1 R, then minus C2 equals to 0. Or we can simply write this one as R squared plus AR plus B equals to 0. So where A is what I have as minus C1 and B is what I have as minus C2. So I'll have this smaller case. So which, what kind of equation is this equation here? If I call this one 4. Equation 4 is which kind of equation? What name do we give to equations which take the same structure as 4? Which kind of equations are of this form in 4? Don't disappoint your high school math teacher. What name do we give to equations which take the form as 4? Boys? Yeah, this is quadratic. So then now, when you have a quadratic equation, how many cases do you consider in terms of the solution? If you have a quadratic equation, how many cases do you consider? So how many cases to consider for quadratic? So there are 3 cases to consider. So case 1, we have 2 distinct real roots. And remember, if I have a general quadratic equation, ax squared plus bx plus c equals to 0, x is given by minus b plus or minus square root of b squared minus 4ac divided by 2a. So what determines the nature of the roots of the equation in this discriminant part, b squared minus 4ac. So when discriminant is positive, then we'll have 2 distinct real roots. So if we have 2 distinct real roots, say R1 and R2, then the solution to the recurrence relation is an equals to alpha 1 R1 power n plus alpha 2 R2 power n, where alpha 1 and alpha 2 are unknown constants, which can be obtained if we are given extra information about the recurrence relation. If you can remember what you learned in ODE, this is the same thing that we are doing, that when you get 2 distinct roots, when you're solving a second order linear homogeneous differential equation, then 2 distinct values of the roots of the characteristic quadratic equation, you get the linear combination as the general solution. So this is what we'll have as our answer to the recurrence relation of degree 2. Then what is another case? If you are solving a quadratic equation, apart from having 2 distinct roots, what else are you likely to get also? Which other possibility are you also able to get when you're solving quadratic? Apart from 2 distinct roots, we can have come on, the stopping of this class depends on your participation. This form 3 work, where you are discussing about quadratic equations. If you don't get 2 distinct roots, what is another possibility? What is the other possibility? Unmute and say the answer. June? June, what's the other possibility? Correct. Repeated root. So we can have one repeated root. So if you have one repeated root, then the solution is an equals to alpha 1 r power n plus alpha 2 times n r power n So this is how we give the solution of the recurrence relation. It's the same thing that you are doing when you are solving ODE problems. If you're solving a second order differential equation with constant coefficients, and you get a repeated root after solving the characteristic equation, you obtain two linearly independent solutions by first multiplying the independent variable by the first solution. So that's why in this case, you have constant times r power n, and then plus another constant, then multiply the independent variable n by the same solution. So to have the two linearly independent solutions. Then case 3, apart from having two distinct real roots and then having one repeated root, what is another possibility? What is the other possibility? Yeah, we have complex roots. So complex conjugate roots. So say R is alpha plus or minus beta I. So in this case, the solution is AN equals to alpha 1 alpha plus beta I power n plus alpha 2 alpha plus minus beta I. Please note that when alpha and alpha 1 or alpha and alpha 2, they are different animals in different kingdoms. So they don't mean the same. So alpha 1 and alpha 2 in this case are arbitrary constants. And this alpha here is alpha and beta, actually the one that defines the complex conjugate roots. So minus beta I or n. So let's give examples. So form the following recurrence relations. So the first one is given by an equals to an minus 1 plus 2 an minus 2 with initial conditions a naught equals to 2 and a1 equals to 7. So this is A. So to solve this, let an equals to r power n be the solution. So then this implies an minus 1 is equals to r power n minus 1, and an minus 2 will be r power n minus 2. That's by definition, if you define an as r power n. So an equals to an minus 1 plus 2 an minus 2. When you do the substitution, you'll have r power n equals to r power n minus 1 plus 2 r power n minus 2. Then for those who are following, we divide through by the next step. Yes. So divide through by r power n minus 2, i.e. r power n over r n minus 2, r power n minus 1 over r n minus 2, plus 2 r power n minus 2 over r power n minus 2. So what is r power n over r power n minus 2? What will be the new power of r squared equals to r power power 1 and then plus just 2. So which is the same thing as saying r squared minus r minus 2 equals to 0. So this is now what we call the characteristic equation. This is the characteristic equation. So then now let's solve this one. By quadratic formula, r will be a minus b plus or minus square root of b squared minus 4ac divided by 2a. So where a is 1, b is minus 1, c is minus 2. So can you substitute in the values and tell me the roots of this quadratic? So what will be the roots of this quadratic? Correct. So R can say R1, we can call it positive 2, and R2 is negative 1. So solution, which I can call the general solution, is AN equals to alpha 1 R1 power n plus alpha 2 R2 power n, which is an equals to alpha 1 2 power n plus alpha 2 minus 1 power n. So if we were not given the extra condition that a0 is 2 and a1 is 7, then we'll stop at this point. But because we have been given a0 and a1 values, then we'll use them to get the actual numerical values of alpha 1 and alpha 2. So a0 is 7, a0 is 2. So mean that when you replace 0 for n, so a0 equals to alpha 1 2 power 0 plus alpha 2 minus 1 power 0, this must give us 2. So 2 power 0, 1, so I'll have alpha 1 minus 1 power 0, 1. So this alpha 2 equals to 2. So we call this one equation 1. And then we were told that a1 for this problem is 7. So where there's n in the general solution, put 1. So we'll have a1 equals to alpha 1 2 power 1 plus alpha 2 minus 1 power 1 should be 7. So this will be 2 alpha 1 minus 1 power 1. So this will be minus alpha 2 equals to 7. Call this one equation 2. So we have now two simultaneous equations in the known alpha 1 and alpha 2. So can you solve 1 and 2 simultaneously and tell me the values of alpha 1 and alpha 2? Solve simultaneously. You can either use the elimination method or substitution method to solve 1 and 2. Alpha 1 is? So alpha 1. Look to your house. I'll check your working. These are just simultaneous equations. This is from one work. If you are participating, I'll have actually stopped. Because you don't want to participate, it will go up to 7. So when you solve alpha 1 and alpha 2, what would be the correct numerical value?
Alpha 2 is 1. Alpha 2 1.
Not really.
Yes.
This may be the only question you can answer in the exam. So ensure that you give it your best. What is alpha 1? And what is alpha 2? Brian and Nyakundi, what is the answer for alpha 1? Which variable is -1? Which constant is -1? Alpha 2 -1, then alpha 1? 3. Therefore now, therefore the specific solution is an equals to alpha 1 is 3, 2 power n, then alpha 2 is -1, then -1 power n. Then you get 3 marks. So example 2, we have fn equals to 6 fn -1 minus 9 fn -2, subject to the condition f0 is 1 and f1 is 6. So remember, when you are writing the recurrence relation, you can use any letter. Any letter can be used. They can use A, B, C, F, or any other alphabet. So there's nothing special with A. So solution, we start by saying, assume Fn equals to R power n is the solution. So then that tells us that F sub n minus 1 will be R power n minus 1, and F sub n minus 2 will be R power n minus 2. So that once you have assumed the solution in the form R power n, then you can always define other sequences for n minus 1, n minus 2, etc. Then you substitute those values in the original recurrence relation. So Fn equals to 6 Fn minus 1 minus 9 Fn minus 2. This now will give us, where there's Fn, we put R power n equals to 6 R power n minus 1 minus 9 R power n minus 2. So which step follows? For those who are following.
Divide by R n minus 1.
Yes, so divide by R power n minus 2, i.e. we'll have R power n over Rn minus 2 equals to 6 R power n minus 1 over R power n minus 2 minus 9 R power n minus 2 over R power n minus 2. We get, so left-hand side, correct, R squared equals to 6R minus 9. Then we just rearrange this. R squared minus 6R plus 9 equals to 0. So this is the characteristic equation. Good. So then now, solve using either quadratic or factorization. So solving using quadratic formula, we get R1 equals to, what is the value of R2? So we are almost stopping, so please participate so that we can finish before 17:40, before 5:45. R1 equals to 3, and R also 3. So this is a case of a repeated root. Yeah. So general solution is Fn equals to, if you remember what you have said in the general discussion. Fn how does the general solution look like in the case of a repeated root? So I'll have alpha 1 r power n plus alpha 2 n r power n. So remember R1 equals to R2 equals to just R is 3. So then this is Fn is alpha 1 3 power n plus alpha 2 n 3 power n. So then if we are not given extra, then we'll actually stop at this point. But because we have extra conditions, then we'll have to go further and get the value of alpha 1 and alpha 2. So we have been told that F0 in this problem is given by 1. So F0 is alpha 1, 3 power 0, plus alpha 2 times 0, 3 power 0. And this would give us 1. So 3 power 0.
1.
So I'll have alpha 1. So 0 times alpha 2 times 3 power 0. 0. So just this alpha 1 equals to 1. And then we have been given F1 is given by 6. So F1 equals to alpha 1, 3 power 1, plus alpha 2 times 1, 3 power 1. This should be 6. So this will give us 3 alpha 1 plus 3 alpha 2 equals to 6. So remember this equation 1, this equation 2. So can you use equation 1 to get the value of alpha? Solve for alpha 2 if alpha 1 is 1. Alpha 2 equals to 1. So therefore, the specific solution is Fn equals to alpha 1 is 1. So just have 1 times 3 power 3 plus alpha 2n 3 power n. So alpha 2 is just also 1. So let's just have n 3 power n. So this will be the solution. or we can write this one as 3 power n, and then plus n 3 power n, or you can write it as 3 power n into 1 plus n. So that will be the solution for that, given the current. Can I assume that if you are given a simple linear homogeneous recurrence relation with constant coefficients, you can get the general and specific solutions? Or I need to give more examples? Should we give more examples, or you can actually, using what we have, you can now go and solve other equations? What did they check? So keeping quiet means that we continue, okay?
No, we can stop at that.
Okay, so then now at your own free time, go and try this. So this is number 3. This is actually the Fibonacci sequence of Fibonacci. And then another one is an equals to 6 an minus 1 minus 11 an minus 2 plus 6 an minus 3, where a naught is given by 2, a1 is given by 5, and a2 is given by 15. Then number 5, fn is given by minus 3 fn minus 1 minus 3 fn minus 2 minus fn minus 3. Then f naught is 1, f1 is minus 2, and f2 is given by minus 1. So work on those problems and do as many other examples as you can. So what is remaining is now to solve the non-homogeneous recurrent relation. Also check out on that. I hope we can stop there.
Can we get the note?
Yes, I'll share.
Okay.
Okay.
Thanks.
Okay, fine. Have a good evening. Okay, fine.